Section 5.2 is about similar polygons. In this section we're going to discuss the definition and then also some different application problems that are based on facts about similar polygons. Alright, so first of all we need a quick review of corresponding parts. So let's suppose that we know that these two quadrilaterals are similar, and just informally, if we want to think about a meaning for similar, we could talk about two things that are the same shape but possibly a different size. Okay, so things that are congruent are similar, and then things that are the same shape but different sizes are also similar. Okay, so in this case it seems like this second quadrilateral is an enlarged version of the first one. They look intuitively about the same shape. Okay, so the congruent angles are indicated, and we want to name all of the corresponding vertices, angles, and sides. Alright, so based on the angles that are congruent, any angles that are congruent to each other would be the corresponding ones. And we use an arrow to indicate that. So we would say vertex A corresponds to vertex H, D corresponds to L, C corresponds to K, and B corresponds to J. Okay. Then for angles, we could go through and just put angle symbols here. So all of those angles correspond as well. And then corresponding sides would run between two corresponding angles. Okay, so since A and H correspond and D and L correspond, then we know that side AD corresponds to side HL. Okay. And then you can just go kind of around the quadrilateral, get the other sides as well. So DC corresponds to LK, and CB corresponds to KJ, and finally BA corresponds to JH. Now notice I'm not saying that these are congruent. They are different lengths, but they are corresponding in that they're sort of in the same location on the quadrilateral. They're connecting the two corresponding angles. Alright, so you want to make sure when we write congruent statements that we do write these with corresponding vertices in the corresponding order. So for example, when we write ABCD and HJKL, then that implies that the letters in the first spot are corresponding vertices and also corresponding angles. Okay? And then similarly, if I pick out maybe like, let's see, we could do maybe B and C and J and K. Okay, then because of the order, that would imply that side BC corresponds to side JK. Alright, so now a formal definition of similar, more than just saying that it's the same shape. We can say that two polygons are similar if and only if these two conditions are satisfied. Okay. All pairs of corresponding angles must be congruent, and all pairs of corresponding sides must be proportional. So not congruent, but proportional. Or in other words, we have, if we looked at the previous quadrilaterals in the previous example, we would have this extended ratio. So AB is to HJ as any of those other corresponding pairs of sides are to each other. Okay, so AB is to HJ as BC is to JK, or as CD is to KL, or as AD is to HL. Alright, and then also notice that in this definition we have the phrase if and only if. So remember, we can read this both ways. So if these two statements are true, then that means that the polygons are similar. And if the polygons are similar, then we know that those two statements are true. Here's an example. This one from the book shows why both of these conditions have to be satisfied, why one of them is not enough. Right, so in figures A and B here, okay, we have a square and a rectangle, and it's true that all pairs of corresponding angles are congruent, they're all right angles, but those are not similar shapes because the sides are not proportional. Okay, so intuitively you can just see that they're not the same shape. And then if we compare A and C, okay, here we have an example of pairs of corresponding sides that are proportional. So let's say, for example, that this square has sides that measure 3, and maybe the rhombus has sides that measure 4. Well, then we can still write a proportion. So for example, let's say like EF is to WX as FG is to XY, right? And then I could keep going and write the other two. But in each of these, no matter how I pair these sides, I'm going to end up with proportions that are 3:4 as 3:4. So that's true. All right, so all the sides are in proportion to each other, but the angles are not congruent. And you can see from the square that they're right angles, and then this rhombus, intuitively, we could have a rhombus that doesn't have 90-degree angles. All right, so if you have two shapes that are similar, we use this symbol. Okay, so a quick review, we have this means similar to or meaning like the same shape. And then we've used the equal to represent things that have the same like length or measurement, we could say. So sort of like the same size, right? And then notice that for the congruent symbol, we're combining those two. Okay, so it's both of those things. All right, so similar shapes are just talking about the angles and proportionality of the figure. Equal to would make the sides, the same length. And then if both of those things are true, then the shape is congruent. All right, so here's our first similar statement in this video. So we have triangle ABC, and you would read this: triangle ABC is similar to triangle DEF, and we're using the similar symbol. Right. So from that, this tells me right here which are the corresponding angles and sides. Okay, so I know, I know A and D are corresponding because they're mentioned first, B and E, and C and F. So we want to use that information to find the measures of the remaining parts of each triangle. So what they mean by that is we want to know all three sides and all three angles in both triangles. Okay, so first of all, I can see based on the way these are oriented that the correspondence is here. So like A and D, B and E, and C and F. Okay, so everything's sort of as expected. Watch for shapes that are flip-flopped, like if they had switched this guy around, then you want to go by the similarity statement to see which ones are corresponding, not necessarily by the picture. Same thing if one of these was flipped upside down. Alright, so since C and F are corresponding, I know that they have the same measure, so C is a 90-degree angle, so that means that F is a 90-degree angle. B and E correspond, so I know E is 37 degrees. Okay. And then I can subtract 90 and 37 from 180 to get that remaining angle, and that would be 53 degrees. Okay, so the angles are done. Oh, this one too. All right, and then I need to worry about the sides. So what we want to do is write a proportion. So what you need is at least one complete ratio, and then one that has a missing piece, and then a number filled in. I should put number symbols here. Okay, so looking at the sides, the complete ratio that I have would be AC and DF. Okay, so one of my ratios is going to be 3:6 as, okay, and then I know the other two sides of the smaller triangle, so I could start with maybe CB and its corresponding side FE. So 3:6 as 4:2x. Okay, or maybe I'll even label this one EF. All right, and then you can cross multiply to solve. So you would get 3EF equals 24, and then divide by 3, so EF equals 8. Okay. Another thing you can do is look for what's called the scale factor or the constant of proportionality. There's some discussion in the textbook about this if you want to look it up. But basically, it's the number that that all of these ratios would simplify to. All right, so if you pick out like the 6 and 3, and if you go like 6 to 3, or if you simplify that, right, that's 2. So the scale factor or the constant is 2, or in other words, all of the sides on the second larger triangle are twice as big as the sides on the first one. And you can also just multiply to get the other sides. Okay, so another way to get from 4 to this side is to find that number 2 and then just multiply 4 times 2. Okay, and then same thing with this last side, so 5 would get multiplied by 2 and this side would be 10. Alright, so that's good enough. We found all of the missing parts, and then we could go through and list them all out if we wanted to make it extra clear, or if you're doing this on homework and you don't have a diagram. Okay, so I would go through like EF equals 8, DE equals 10, and then I would give the measures of the missing angles that I found and so forth. Alright, so let's solve an algebra problem using similar triangle information. So usually this involves setting up proportions with the sides. Okay, so we know triangle ABC is proportional, or I'm sorry, is similar to ADE. Okay, so let's find those. So we have ABC is this guy, and then ADE is this smaller one. Okay. A hint for you, if you're having trouble seeing these and seeing the proportions, maybe redraw the diagram with the similar triangles next to each other instead of nested inside of each other. Alright, and then they make this extra clear. Angle ADE, right, is congruent to angle B. They didn't need to specify that since it's implied in the way that the vertices are ordered in the similarity statement. But now they've made it extra clear. Alright, so we know that DE is 3, AC is 16, and EC equals BC. Okay, so we want to find the length BC. Alright, so everything's labeled in the diagram, and we want to try to keep the variables to a minimum. So since EC and BC are the same, we can label those with the same variable x. Alright, so we want to solve to find the length BC. So what we want to do is set up a proportion that has BC in it. Okay, so I'm just going to stick that in there. And now BC is a side on the triangle ABC. Right. So I'm going to put my triangle ABC information in the numerators, and then I'm going to put corresponding sides from triangle ADE in the denominator. Alright, so BC corresponds to what side on triangle ADE? Well, that would be side DE. Okay, so BC would be to 3 as, and then we need another ratio. So I need another side from triangle ABC, and I don't have this side, so I'm going to use the other one that I do have, which is the 16. Okay, and then which side on ADE does that correspond to? Well, the 16 would correspond to this one here. All right, And we don't know the length of that, so we need to label that, right? So I'll call that AE for now. But now if I want to solve this proportion for BC, I need to figure out how to get this proportion down to just one variable. So we're going to try to label things in terms of x. So BC is actually equal to x. Okay, so we can fill that in. And then AE, what I want to do is try to express that in terms of x. All right, well, if this whole side length here is 16 and this piece is x, then AE is 16 minus x. Oops. Okay. So x is to 3 as 16 is to 16 minus x. Alright, so we are all set up to solve, so the next step is to cross multiply. And we're going to get x times 16 minus x equals 3 times 16, which is 48. And then we distribute the x on the left, so you get 16x minus x squared equals 48. And this is a quadratic equation, so we can either choose to factor this or use the quadratic formula. We can't square root it because it's got this x term in there. Alright, so either factoring or quadratic formula requires setting the equation equal to 0, so that's next. Let me erase that. Okay, so I'm going to move the x squared and 16x to the right so that I can get the x squared to be positive. Okay, so add x squared, subtract 16x, 48's still on that side, and then that equals 0. Alright, so let's try factoring first. Maybe the numbers work out nicely. Alright, so I know it's going to be x and x to make x squared. And then 48, we have some options, so we could do, let's see, 1 and 48, 2 and 24, 3 and 16, 4 and 12, and you could just keep on going, 6 and 8. And then here's my tip to exhaust all the factors. You would go until you start repeating. So you just start with 1, and then you make like one column with the factors increasing. So after 6, 7 doesn't go into 48, so 8 would be next. And then you can see we have a repeat just in a different order. Okay, so I know from now on any other factors are just going to be repeats of the ones that I have. Okay, so we want a pair of those that multiply to be 48, and we could do 2 positives or 2 negatives, but I know that they have to add to be negative 16. Okay, so it looks like I want 2 negatives, and 12 and 4 are the ones that work. Okay, so that means that x minus 12 equals 0, or x minus 4 equals 0, and then x equals 12, or x equals 4. Okay, so if you refer to the diagram, x is a length, so we do want to make sure that it is positive, and both of these are positive answers, so we can't rule any out for being negative. And then we also want to make sure we answer the question. So BC actually is x, so either of these are possible answers for BC. So we actually have 2 answers here. BC could be 12 or 4 based on the given information. Okay. And then here are the 2 diagrams that show that. So if BC was 4, the figure would look like the one that you were given originally. And then if BC were 12, it's still possible. We just need to sort of rearrange and redraw the diagram to reflect those lengths. Alright, here's another problem using similar triangles. This technique is called shadow reckoning, and it goes back to the Greeks. And it's still kind of handy. I mean, if you think about it, maybe it's not absolutely essential now, but let's say that you did want to know something like the height of a flagpole, and let's say you can't climb the flagpole and there's no one around to ask how tall it is. Not that you would ever definitely need to know the height of a flagpole, but if you're curious, this is a nice way to figure it out. So this is a similar triangle situation if you look at the triangles formed by a person and the shadow, and then just the hypotenuse connecting them, and then the flagpole and its shadow, and the hypotenuse connecting those. Okay, so we're operating under an assumption that the rays of the sun hit these two things at the same angle and make shadows in a proportional way. And we can assume that because this person could stand pretty close to the flagpole so that the sun would be hitting at the same angle. And then since the sun is so far away from Earth and the distance between the person and the flagpole is so small compared to the distance from the sun, as far as accuracy goes, these are close enough that we can just assume that the angle of the sun is close to, it's not perfect, but close enough to being the same angle. Alright, so under that assumption, here's how this would work. The person would know how tall he or she is. So this example is Darnell. So Darnell knows he's 6 feet tall, and he would sort of mark where his shadow falls and then measure that out. Okay, so maybe he stands in one spot and like puts a little mark on the ground. Maybe he sees where his shadow is, and maybe a friend puts a rock down or something, and then they can measure that distance. Right, so that's possible with a tape measure or a yardstick or something along the ground. And then same thing for the flagpole. Maybe you can't climb it to measure its height, but you can at least measure its shadow. Okay? And then under the assumption that these form similar triangles, then you can just set up a proportion to solve for the height of the flagpole. So you would say the man's 6 feet height is to his 9-foot shadow, as the flagpole's height is to its 30-foot shadow, and then you could cross multiply to solve. All right, and you would get the height of the flagpole is 20 feet. Okay, so not terribly difficult, but it's a kind of interesting technique. So try it sometime if you're interested. You can do this with a really tall tree or something like that. Okay, so that's section 5.2. There was some other information in this section. One thing we're not going to do is prove that polygons are similar. We're not going to do proofs for those. So just focus on the examples that we've talked about, mostly from this section, understanding the definition of similarity, how to write those corresponding statements, okay, like which angles correspond to each other, and then using proportions to solve for missing sides, either just in a geometric problem or in a word problem.